Let me also just say that if you have questions, but for whatever reason your audio is not working or you'd prefer not to ask by audio, feel free to type your questions in the chat box. I'd be happy to read them for you. Okay, so I think our first question, I think Alyssa has a question. Alyssa?
Thanks. I really enjoyed both the talks. I had a question for Eleanor. So I'm just lowering my hand. Yeah, so you were talking about leaning towards using like a Lewisian conception of functionalism here. And it was just a clarificatory question. If you could say more about like why you think that in particular is the right kind of approach. Like I don't know how fine-grained you're distinguishing different views about functionalism. Like, you know, just a couple of, one is like Lewis's picture is holistic in a way where you define all the terms together. I don't know if that was something that was appealing to you. Another thing that I wasn't sure if this was a good thing or a bad thing for you in the way you want to be neutral about whether or not the realizer is more fundamental than the space-time concept, is the way Lewis kind of thinks about functionalism as giving an account of some concept in the language of what he calls an old theory, a theory that like we have, you know, antecedent familiarity with. And so anyway, I was just hoping you could say more about that, why the Lewisian conception is the kind of the right approach for characterizing the way in which we should think of space-time as functional.
Yeah, I mean, I think my primary motivation is to kind of get away from some of the kind of role functionalist baggage of philosophy of mind. So it's partly to give us a kind of familiar watchword, and also to ground it as a theoretical relation. So to make it very clear that what you're trying to do is analyze the space-time concept, right? What we're trying to do is work out what the appropriate application of a concept to a theory is. And I think that a Lewisian approach to theoretical terms is the one that everyone's most familiar with to do that. And certainly the emphasis on definition is also helpful. Yeah, I mean, I think that's you know, I don't know if there's a precisification of those views that would be slightly different from Lewis's that would be better for my purposes that you're thinking of.
And you liked it because it was a realizer as opposed to a role functionalism, because you wanted to like depart from the idea that the functionalism would give you some kind of like a dualism or some kind of a non-reductionist metaphysics. Yeah.
Yeah.
Okay.
Yeah, that's exactly right. So I think that, I mean, even the role realizer debate can go very heavily metaphysical in philosophy of mind, right? But I don't think that the issue here is whether the property of being a space-time is the property of being a role, or the property of, or the thing that realizes that role, right? I don't think that's the right locus for the question I'm interested in is the question of how we identify space-time in theoretical structures, right? And that's very much a question of finding a realizer of a particular kind of role.
Great, thanks. I think Elise has the next question. Elise?
Hi, yeah, thanks for a suite of really lovely talks. My question is for Alyssa, and I guess I have two of them, so it's a choose your own adventure, just answer whichever one you like better. My first question is, I'm really sympathetic to your idea that if emergence is supposed to be that from whence other structure is emerging, that if there's some preset, or the metric in particular, if entanglement relies importantly or irreducibly on some notion of distance, then that's a problem. But might it be that the way we're using distance when we discuss entanglement relations is metaphoric, or just some not vicious in some way, an artifact of the way we discovered entanglement relations or talk about them in pragmatic circumstances? So that's one question. The other is, you partially answered this or began to answer this when David asked his question, but what would count as maybe sufficient or necessary conditions for a proper emergence claim? Like, what would make you happy to see in the literature?
I don't know. The answer to the second question is I don't know. It just seems like if the account, so I feel like in the case of black hole entropy, the Sorkin and Bombelli argument is clearly assuming that it looks to me like the facts about distances are needed to ground the facts about the entanglement. And so in that case, if that's correct, then you don't have a case of emergence. Yeah, it's more just, that's going to rule it out. What would, confirm it? I don't know. I guess, the right thing to say would be the fact that you have the link does confirm it. It just gets undermined by the fact, just if we had this entanglement distance link, that would confirm an emergence hypothesis, since it would make it more likely. But it just seems like it gets undermined that if you think that the correct explanation, metaphysical explanation for the entanglement is presupposing facts about distances already. For the first question, I don't think it's metaphorical. So I guess I do want to look at those explanations in more detail. So I just this is really new work for me. And so I was hoping people would press back on the way that I was drawing metaphysical explanations from the Sorkin-Rovelli argument and say something like what you're saying. It's possible, you might just say there's we can do a ladder kicking, in order to compute the, in order to compute the entanglement entropy or get a kind of sense of approximately what the values it would take, we need to make these assumptions about the states being Hadamard and then so on, but then we say, but of course those distances are not fundamental. So that was a good heuristic to use to get us to the right value for the entanglement entropy, but then, that's not really part of the metaphysical explanation. So I do think that that's a move that I would assume somebody that wanted to take on that kind of explanation and import it over to the ADS CFT case would say something like that. And I think that that's fine. I guess what I'm saying is if you do that, then I would want well, then what is the metaphysical explanation for the entanglement entropy, the entanglement entropy having these values? It's it's a thermodynamic notion. It doesn't seem in general, there are kind of explanations for why we have these kinds of, features have the values that they do. So what is the metaphysical explanation for that? And so the Sorkin-Rovelli argument interpreted literally gives you a story. And so there would have to be some, I feel you would want some other kind of story. And that's kind of what I try to leave open in the end. But yeah, good. Thanks for pressing me on that. I feel that more work needs to be done there. In the condensed matter case, so I think that things are a little bit more straightforward, where you really are the area. Look, I'm not a physicist, and this is really kind of challenging for me even to understand what exactly, how exactly the argument is. But either in that review article, it's being emphasized over and over again that the case where you get the area laws are cases where you're assuming locality of the interactions. And so that looks to me again, you're getting these area laws, you're getting this kind of connection when you're assuming facts about what are nearest neighbors, and that to me looks like facts about distances. That I think is a little bit more straightforward conceptually what's going on, even if the physics isn't straightforward.
Thank you.
Great. If it's okay, I actually have a question for Alyssa. So my own views on questions of emergence of spacetime for more fundamental theories are I'm non-committal, but I do think there's an interesting additional argument that could be seen as undermining the claim of emergence. Many of the constructions that one sees in these holographic dual pictures, I think that the picture of the EDS eternal black hole and thermofield double state gives a particularly nice example of this. Is that so? In the field of quantum information theory, there's this theorem, the Stein-Spring dilation theorem, which says that if you have a quantum channel, some quantum system that undergoes a possibly non-unitary process, as long as the process is sufficiently nice, one can always, as the saying goes, go to the church of the larger Hilbert space. You can purify the system by adding on a fictitious additional system. It's called the ancilla. And then what was potentially a mixed state for the original system is now a pure state in this formally enlarged composite system. And the original dynamics that might not have been unitary, as long as it's sufficiently nice, it has to be completely positive trace preserving, can be enlarged to this larger composite system to a unitary, a form of unitary evolution. This is very reminiscent. I mean, it may not be exactly the same thing. Maybe it is. Maybe there's some sense in which classical general relativity in the bulk is some kind of coarse-grained, hydrodynamic description of something more fundamental going on, but maybe something that's not exactly unitary, but it can be purified by adding on an ancilla, which is the boundary theory. From this point of view, there is no sense in which the boundary theory is more fundamental or that the bulk theory emerges from it, right? It's playing the role of a purification sort of ancilla, like a system that you augment formally to the system to render it pure and render the evolution unitary. I mean, I don't have a precise question exactly or argument here, except to say that there are reminiscent stories that happen in quantum information theory that look like taking a description that is not seemingly unitary and maybe under some coarse-grained approximation might even look classical. It could be entropy generating, like black hole formation is entropy generating, and recasting it as a unitary theory with the addition of some ancilla, some additional system. But we wouldn't in that case say that the ancilla is sort of fundamental and the original theory was emergent. I don't know if this seems reminiscent to you, but or if you have thoughts on this, but I just thought it was an interesting correspondence that I noticed.
Yeah, I mean, I wasn't thinking about the CFT as playing, the boundary as playing that kind of role, but I mean, I feel like the starting kind of intuition that's not, the starting intuition that the role that it's playing, like, in general in holographic theories doesn't look like at first like that's something that's more fundamental. It looks like it's the kind of a boundary on what's going on. And so that's kind of why at first, at first I'm like, okay, I want to understand better, like why are we viewing that as fundamental? And so honestly, that's not something that I really discussed too much in the paper. I was just kind of saying, look, at least these results on them, I wanted to see, did these results by themselves or the way that these results are kind of justified and explained support an emergence hypothesis? And I was led to the conclusion that no, and in fact, it seems like the explanations for these results are in tension with the emergence hypothesis. But I have to say, I think a lot of metaphysicians first look at this as it looks like the two theories are equally fundamental, if anything, or equally non-fundamental. Yeah.
Thanks. So the next hand I have is Isaac Wilhelm.
Hi, thanks. My question is for Eleanor Knox. So thanks very much for your talk. That was super interesting. I guess I had a methodological question. Basically a question or a concern about what might be a small feature, I wasn't quite sure, of your approach to space-time functionalism. So a few times in your talk, and then when you were responding to Dave's question, you expressed what I was interpreting as suspicion over intuition trading, like whether intuitions about whether this or that counts as a case of space-time or not. And I wasn't really sure why you were that suspicious of it. And the reason is you think that space-time is whatever plays a certain conceptual role. So space-time is intimately bound up with our concepts. And then I was thinking our intuitions are going to play a pretty big role in determining what space-time is, insofar as intuitions are like a manifestation of what our concepts are. I mean, I can think of maybe two ways of getting at what a concept of space-time might be for a person. You could just ask them and they'll just report their intuition about what that is. You could do a big population-wide survey and try to get like what the average person's intuition about space-time is. But I thought we might not want to do that, at least not over the average, over like the whole population, because that'll include a lot of stuff that we think space-time doesn't have, the average person's conception of space-time. So I guess my question was just, did I have that right? Were you suspicious of intuitions and intuition trading as a way to adjudicate theories of like space-time functionalism? And if you are suspicious, why isn't that a kind of like a problem for that very project?
Yeah, so I am suspicious, and I think you should be. So I think there's a danger that, I mean, look, I mean, of course, we could have a big debate exploring mine versus Dave's conception of space-time, but I'm not sure that anybody here should read that paper, right? Like, I mean, we could find out that our intuitions disagree on a particular space-time, but it's not obvious what we're disagreeing about. So, and I can completely see that if you think that that's not something we could disagree about as a factual matter, you might be concerned about the debate. The reason I think that we should be interested in the space-time concept is I think that it has this tie back to, this very particular tie back to the empirical content of our theory. So this isn't a hugely anti-realist point. It's just that once you've decided that the structure of your theory and that, you know that the mathematics represents, etc., you might ask, well, what else is the point of adding? And this thing here, it represents space-time. And I take that to be a really interesting question, in part because space-time has this particular role to play in how we empirically interpret our theories. So I say we read off, there's kind of, you can think of there being kind of a long and a short way to get to a measurement result. You could calculate, a la Harvey Brown's kind of ideas. You could sort of think of taking rods and clocks and your measuring devices as fundamental and try and work out all the dynamical equations that govern them. Or you could just make a bunch of assumptions about space-time. So space-time has this very particular empirical role. And so the reason I think that saying, oh, I've got this theory of quantum gravity and I think that this thing represents space-time in the relevant way is important is largely because of that empirical connection. I'm more skeptical that say, now, I think we can have a debate, and I think there are ways to interpret it as a fruitful debate in a theory where we don't expect the spatiotemporal notions to link up with empirical content. I think that we might, so suppose you're looking at things like ADS-CFT correspondences and you're wondering about spatiotemporal variables in each one, and you don't think that those are going to directly correspond to anything like the empirical space-time that we live in. You might nonetheless think there are interesting debates to be had because the assumptions you make about what variables represent space-time will affect the ways you model your physics in various important ways. So I think those are all important debates. Despite being a perfectly scientifically realist and somewhat interested in metaphysics person, I'm very dubious that when we get to debates that are very far from empirical debates, that exploring the ways in which your and my concepts do and don't apply is telling us anything very significant about the world. So I think there is a way of kind of reconciling that skepticism with the project being interesting.
Great, Isaac, you're all set? Okay, next on my list I have Makinde.
Hi, my question's for Alyssa. First off, thank you so much for the talk. I really enjoyed it. I actually happen to be a condensed matter theorist. So first off, I have a few points that I think might be helpful or interesting for you. And then some general questions. Well, the first of which is one slight subtlety I might look into is the local interactions that give rise to an area law. There's actually a bit more going on there. You typically see this in local interactions, but the area law can and is expected to be violated for fermionic interactions. Now there's an extra bit of non-locality if you want to think about the degrees of freedom at play with fermions. But I think it's something worth being a little more careful about. Right. I forget the second point that I was about to say, so I'll push that to the side. But the question that I had was more in line with what would you be satisfied with to see emergence. I wanted to ask if you were particularly looking for a dynamic metric, or if you were looking for truly some emergence of a metaphysical concept of space and time. Because if you're looking for that kind of like a conception of space and time, that seems like a very, very strong ask to find a theory that has nothing like it, even a quantum theory, and to have that emerge. If you're asking for something more like a dynamical metric, then something in the lines of, say, Professor Carroll's work, where he's looking for taking local Hamiltonians and that giving rise to some kind of dynamic metric, seems like it would be a potential answer to your theories, or to your quandary. And I've just remembered the additional bit I wanted to add, which was one thing that I think would be very important, or at least interesting to me, is the study of different entanglement metrics. I'm sure many people here are aware, but the entanglement entropy that you're using also captures classical correlations. So for example, if you look at a CFT that's in a thermal state, or if you have a mixed state, as you said, then you won't only capture the information from entanglement. You'll get lots of other classical correlations as well. The negativity that you mentioned, though, in I forget which paper, that exclusively captures quantum correlations, or at least it provides a bound on the quantum correlations. That's a relatively new metric, but it's one that I think is a bit more useful if that's what you're looking for. I've spoken long enough, so I'll let you respond to the dynamical or metaphysical space-time question.
Thanks a lot for all those comments. If you could, if you do remember what you were going to say and you want to email me, I'm at UC Davis, really easy to find. So, you know, I would love to get any more feedback you had. Yeah, so I didn't talk about fermions. The case that I focused on was the case, it was a case of a bosonic chain. And so I just wanted to show like a situation where you would have an area law confirmed outside of the ADS CFT context. And so, yeah, so I actually don't even have a discussion of fermionic case, but in the paper, but I think, yeah, it would be good to kind of be clearer about the situations in which you have the area law satisfied versus the cases where you get kind of divergence from that behavior. And sure. Okay, yeah, so, oh, your question, okay, so, right. So yeah, the logarithmic negativity that was talked about in the condensed matter part of the presentation also. And that's good to know. I didn't know. I mean, of course, I'm aware that the Neumann entropy isn't just capturing entanglement, but I didn't know that the logarithmic negativity played that role, and that's really good. That's really helpful to know. Yeah, so Sean's work, like, absolutely. I mean, I think Sean's work is like capturing a genuine sense in which you have space-time emergence from a fundamental metaphysics that's not spatiotemporal. I mean, his fundamental picture is in Hilbert space, and you've got this, you know, he defines, you know, he has like these nodes in the Hilbert space, and there are relations of mutual information. I didn't talk about that just because I did have it in the paper presentation originally, but it was an hour and a half, so I had to cut that out. But absolutely, like, that's a picture that's super clear. It's a case of emergence. And I think that in Sean's work, like, he gives other kinds of motivations for thinking that the space-time is emergent. The kind of motivations were similar to the kind of motivations that David was talking about in his question, David Wallace earlier in his question. And so I think that that would be a way of kind of motivating why we should think about the entanglement entropies as more fundamental than the metric. All I'm trying to do in this paper, I acknowledged I was going to be a party pooper, and in the beginning of the paper, but I'm really not a party pooper. Like, in general, like, I'm super intrigued by Sean's picture. I'm super intrigued by the idea that this space-time is not fundamental and emerges from some more fundamental, quantum structure. Like that's really cool. And I want to understand that better. The first thing I want to do, though, is understand the physical motivations for it. And so I just wanted to be really clear about, like, how do these area laws get motivated? When do they obtain, and what circumstances do they obtain? And which circumstances do they not obtain? And then what kind of explains that metaphysically? And what I was trying to show is, in the cases where you get them, and you're right, there are more cases that I didn't talk about where you don't get area laws. For the cases where you do get them, there are always these assumptions going in about distances. And so it doesn't look like just saying, like, look, you have these area laws, here's why the area laws obtain, therefore you have space-time emergence. There's like a little bit of a tension there. And so that's kind of the idea. So then what you would have to say is something like I was saying to Elise. You would say, look, the standard kind of explanation for why these entanglement entropies have the values that they do does appeal to distances, but that's just a kind of way of having us see why the entanglement entropies have the values, or whatever entanglement measure you're interested in, why they have the values they do. But that's not like the metaphysical story or the metaphysical explanation for like why those entanglement entropies arise. You might say, well, that's just primitive. That's just a primitive metaphysical fact. And then you have to motivate, well, why do you think that? Why do you think that these entanglement structures are like the more primitive metaphysics? And I think that, I've seen Sean do that. And in the motivations, I read as philosophical, but that's not a negative. I like philosophy. So thank you for all of that. I really appreciate the feedback and pointing me to more to look at.
May I follow up very quickly, Jacob? Okay. Just to be clear, one of the key parts of Professor Carroll's work is that all of the Hamiltonians looked at are local, and so there does seem to be some kind of, although less explicit, space-time structure. Again, even if it's just reduced to this locality constraint. So wondering about your thoughts there.
Yeah, so, well, what it looks like, so what I would want to say is, what does that mean? Like, what does that mean to say that the Hamiltonians are local? So you have a certain kind of Hamiltonian you write down that you might say, that corresponds in like some kind of effective description, or some less fundamental description to a kind of space-time structure in which these things are closer to each other than these things, but that's not the kind of fundamental story. So I think that that's still compatible with an emergentist metaphysics. I think that's fine.
Thank you.
I see that, I think Sean's not here anymore, but in his defense, I should note he has a recent paper with Ashmeet Singh on mereology in the Everett interpretation, where he tries to derive, a canonical decomposition of the universe into subsystems, that would have with it an emergent notion of locality, right? He considers Hamiltonians, and tries to argue that different Hamiltonians naturally lead to different notions of spatial dimension and a natural or preferred decomposition of the universe. I mean, so you can go look at that paper. It's relatively recent, and see how he tries to address that question. I think the next question I have is Guido.
Again, a question for Alyssa, and I really enjoyed your talk. It was very helpful, but in a sense, it's again the same question. Just wanted to press you a bit more on this point of the locality. Now, precisely because nearest neighbors. that can be thought of as, we've got a certain structure of interactions, and from this structure of interactions, we can read off some relations that look spatial. I was just wondering, maybe the devil is in the details. How do these arguments exactly work with getting from the locality of the Hamiltonians to the area law and so on? But I had a bit of an alarm bell. Which way does it go there, really?
Wait, so is your first of all, it's nice to meet you in person. Is sort of in person. Is it, so are you're thinking that there is a way of understanding local neighbors? So like these two are local neighbors, these two are not, that isn't like fundamentally spatiotemporal? I mean, that the concept of itself of nearest neighbors, you're saying the concept itself of nearest neighbors is not a spatiotemporal notion?
Well, that it need not be fundamental.
Oh, yes.
You have interaction between these two and not these two, so these two are nearer than these two.
Oh, yeah. Yes. So I think that's, so then the question is, how do you tell that story? Tell the story. Maybe, Sean's picture is going to tell us how that, how that works, because he's just going to kind of flip the order of metaphysical explanation that I'm antecedently working with. And I'm not like, let's do that. Let's think about that. But, again, it's just like the kind of straightforward, first pass kind of understanding of what's going on in the condensed matter cases. That's where this kind of locality is playing a role. And then the kind of thing where it's not exactly locality of interactions, but it's the kind of, leading order behavior for the Hadamard states in the black hole entropy case. Like it looks at first.
That looks like a different case. I mean, I don't.
Yeah. And so then you need
more holes in that.
It is a different case. Yeah. It took me a while to understand what the different case was, but yeah, it's a different case. So yeah, okay. I'm in agreement with you. It's just now we need more argument to kind of say, why should we flip the order of explanation in that way? And I'm also not trying to say, I hope that I didn't give this impression. I tried to acknowledge Sean in the beginning because I've been really inspired by his work. I think like he has done this and he is motivating it. And I'm just trying to present it like, let's get clear on how the argument looks. And so, I mean, one thing, I'll just make an analogy with like my work in like the wave function realism and that whole debate. Part of what I've been trying to do there is try to argue that the case for that way of seeing space-time is not fundamental, or, space is not fundamental, is actually like more of a philosophical argument. And it's not just like, you look at quantum mechanics and there's just a wave function. And so, it's just straightforward. Like if you understand physics, you understand the world's a wave function. There's kind of more that needs to go into that argument philosophically. And that's kind of what I'm trying to push. That's kind of what I'm trying to push here, is that when you look at the physical motivations that are underwriting these area laws in the different cases, they're actually not like on the face of them supporting space-time emergence. They look in some sense incompatible with it. So then if you want to say, well, the locality is really explicable in terms of some more fundamental facts about entanglement or something like that, then you've got to motivate that. And that probably involves some philosophical considerations in addition to, probably the kinds of things like Karen was talking about, like unification and whatever. So, but thanks.
Yep, thank you.
Next, I have Jerome.
Hi, so thank all of you for your talks. They were quite interesting. My question is for Karen. And so I was wondering why we sort of need this quantum in some sense, sort of constraint when we already have several of these other criteria that might otherwise entail it, or be sort of useful enough. So if it fits with the sort of empirical results that we have, makes useful testable predictions, and works on certain scales, I don't, in principle, see why we need this additional constraint, other than maybe to sort of ensure that it fits as quantum gravity rather than some other kind of gravity. But yeah, I guess I'm wondering, if we were to have something, like, what would the hallmarks be of it being quantum? I know somebody brought that up earlier. And why would those be sort of significant to solving the sorts of problems that we want to broadly solve with regards to quantum field theory and general relativity?
Ah, right. So as long as it satisfies kind of the other constraints that we have a theory that describes the domains where those two theories are supposed to both be necessary, without the theory itself having to be quantum in any sense. Yeah, I think that's a good point, especially when I've left it so vague what being quantum means and however you want to fill it in. Maybe it could actually be an idea to take it off the list and then evaluate it separately before deciding how to put it back in, especially when yeah, there's so many different ideas about what that could possibly mean. It might like be less helpful to include it as a constraint than anything. Yeah, so that could be a good point. I have to think about that a bit more.
Thank you.
And next on my list, I have Dave.
Yeah, I guess I did kind of want to get into one thing about with Eleanor about the orientation thing. Thanks to start with for all three great talks, by the way. So Eleanor, I guess I'm a little puzzled about why you think your response to the second point about different forces having different, like effectively for you, different classes of inertial frames, why that's supposed to be compatible with your universality posit, you know, which I take it is that all the forces are supposed to identify the same classes of frames as inertial. It seemed like what you're saying is acknowledging that they don't, and then saying that that's compatible with your view, but I guess I don't get how it is compatible.
So I wasn't saying they have different classes of inertial frames. I was saying the class of inertial frames is the class in which all of the laws take the same forms. And so it's the most restrictive symmetry group, right? I mean, it's not, I mean, obviously some theories have wider symmetry groups than others. And so the point is, if the weak interaction didn't exist, well, then you'd have a different overall symmetry group for the laws. But we're asking the question of, yeah, I mean, there are scale invariant and non-scale invariant laws. There are, yeah, there's all kinds of differences in symmetry groups of various laws of physics. And the group that picks out the inertial frames is the symmetry group they have in common.
So in what sense does your, like, what do you intend that universality constraint to mean? Because like I guess I just don't see.
Well, what I just said is exactly what the universality constraint means, right? So the inertial frames are the ones in which all of the laws of physics take the same form.
All of the, oh, okay. So it's not all the forces agree on what the frames are, which frames are inertial. They all individually agree. It's that taken together, there is some set of frames that is inertial according to like the conjunction of all of them.
Yes, yeah, that's the thought.
Interesting.
So that's, yeah. So I mean, you can think of all, without the weak interaction, right? You can think of lots of cases where some particular set of laws would have a larger symmetry group than others.
Yeah.
Let's change the space-time structure. So I think that accords with our normal notion of space-time structure.
So, I mean, what would be an example, I guess, of like a kind of like messed up theory that violated that condition?
I don't think it's a condition that a theory could violate, right? Because this is just a constraint on what you call space-time. It's just a fairly standard universality thought of space-time. So you could have a theory. You could have we could have Galilean invariants. You can show any theory, like Poincare invariants for all of our theories except one, which actually flashed a unique number for every region in space-time, and thus violated all of our symmetries, right? And you would have to say something pretty weird about space-time if you decided that you had a genuine theory that wasn't translation invariant, or you didn't have any of the other invariances we normally associate.
Yeah. Interesting. Okay. Thanks. Yeah, I feel kind of mortified in a way because I really misunderstood what you meant by that condition.
Well, yeah, I'm sure that's my fault.
Great. So the next person I have is Carlo.
Let me not repeat the same mistake and not to unmute myself. Okay. First, Alyssa, first a short comment. When the Ryu Takanagi result came out and the claim that followed that space-time emerged in some sense, this is evidence for that. We in our community looked at those, and there was a lot of discussion, and we got to exactly the same conclusion as yours, that you presented in a much more clean and complete way than we did. So I just wanted to tell that to you, which means that either we're both wrong and not understanding something, or we're both right.
I'm in good company.
Yeah, right. You're in good company. But the point I want to make, it's related to a number of questions by Elise, by McKinnon, by others to you. It also touched about Eleanor's point, which is the following. Some people ask, well, what would be an example of emergence of space-time? And besides speculations and tentative theories, I mean, among the few theories, the few tentative theories, of course, quantum gravity that are on the market, loop quantum gravity, in some sense, has a precise notion of emergence of space-time in the following sense. Forget the heuristic derivation of the theory, just take the theory. And in the theory, there is a precise sense in which there is no space-time. Now, one way in which we understand emergence, generally, I mean, we have condensed matter people and so on, we can easily talk about emergence when there is an approximation, a limit, where there are some concept notions, mathematical structures that become relevant in that limit that make no sense before that limit. I mean, think about hydrodynamical limit and similar. Now, an example of that is the quantum to classical limit. I mean, in one sense, classical theory is a limit of the quantum theory. So if you think about electromagnetism, quantum electromagnetism, you have a Hilbert space of photons, and you definitely have no four-dimensional continuous Maxwell wave, of course, because that's not compatible with no trajectories in quantum mechanics. So the four-dimensional continuous Maxwell wave emerges from the quantum dynamics of photons, of discrete photons, in some limit, and is a very good approximation, is a very useful compass. Well, that's exactly the way in which the four-dimensional space-time continuous metric of general relativity emerges from the Hilbert space and the observable algebra of loop quantum gravity in exactly the same manner. So here we have a Hilbert space, well-defined with observable algebra, with all its structure, no continuous four-dimensional metric manifold whatsoever, but then in some limit, there is a classical approximation in which you see emerging the structure. My question is that, isn't this an example of emergent space-time? And I want to make a last comment connected to what Eleanor says. Of course, there's a huge ambiguity in the use of the notion of space-time and the use of the expression space, and that's not even enter to time, which is even more. So we can always give in some theory or some say, oh, wait a minute, look, there is something that we might call space because it has something in common to the use of the notion of space that we have in dealing with another theory. So when saying emergence of space-time, I think one should be careful by saying, what are we talking as emergence? There is a general notion of space, which is before Einstein, before Newton, it goes back to antiquity, which is who is next to whom. I mean, localization, what is in the theory something that says that things are localized. You might find something like that in a theory without necessarily having a four-dimensional space-time in the sense. So you might have a different notion of emergence. That's what seems interesting for me to articulate, the different use of space and time and the different way things we do with these concepts versus how they emerge from the theory which is considered more fundamental, not the fundamental theory, because I listened to Karen, in how these notions might not appear in a more fundamental theory. So look, quantum gravity, I think there is a precise articulation of all that and a precise sense in which the four-dimensional space-time that we're familiar with from general relativity or from special relativity emerges from a more fundamental structure, which is just a non-commutative algebra operators and Hilbert spaces, where it's not there.
Yeah, so I was just working, so I think that that's one, okay. Yeah, so I was trying to say in the beginning, I thought that it was clear that in these other approaches, like in the case of loop quantum gravity, you did have good reason, and like I mentioned, causal set theory also is good reason to think space-time is emergent. And it's nice to have like a really clear picture of what that sense of emergence is there. I think that perhaps in these other kinds of approaches, I mean, I didn't talk about Sean's approach really in much any detail in my talk. A lot of people are bringing it up in the Q&A, and I wish he was still here to talk about it. But I think I think that there will be a sense, like that kind of sense of emergence of a kind of classical space-time in that approach, but there might be something more than that, and so and I want to allow that would be a sense of emergence as well, because in those papers of Sean with his collaborators on this kind of picture that people have been talking about, he has this kind of Hilbert space structure. And then he talks about, he separates that into these kinds of regions and talks about relations of mutual information. And a lot of people have liked to talk about mutual information instead of talking about like entanglement entropy or some, these other measures of entanglement that I talked about today, because the kind of formal features of mutual information are look like a space-time kind of relations. Like, for example, it's for entanglement entropy, things could have the same entanglement entropy even though they're distinct regions or something like that. Or sorry, the entanglement entropy might be 0, even though we shouldn't think that it's like one kind of region. So anyway, I think that there might be a different kind of emergence that is also kind of cropping up in that kind of picture. But I just was trying to, use the term emergence in a looser way, at least in this paper, just to kind of say like, what you have emergence when this set of facts is arising from this other set of facts, or obtains in virtue of this other set of facts, or is grounded by, and it's definitely a virtue of an approach if it's like saying that space-time is emergent and then being super clear what that means. So yeah, thanks.
But why, if I just very shortly, why wouldn't your previous criticism to the Takanagi structure work equally for what you just said of Sean, given what Guido and Mackinder said, namely that what is happening in Sean is that there is a Hamiltonian, there is that couple subsystem in a certain manner, and this coupling determines an entanglement, because that's what happened. So which is the same, sorry, which one you want to take first?
Yeah, so he has a, I think, I don't see this in these papers that are published in physics journals, but I've seen when he's presented this to philosophers, he kind of gives a motivation for why you should take the kind of, I don't know, the quantum theory first. And he talks about, you know, that we should be thinking that there are superpositions of different spacetimes. That's something that we should be starting with. And I thought that that's kind of where I was thinking that kind of motivation was coming from. That's it. But I don't want to, I can't speak for Sean. Maybe there should be another session where he talks about that part of his work. You know.
Yep.
I'm actually going to put a link to the article I mentioned that Sean just put out with Ashmeet Singh, because I think it may be relevant to some of these questions. I'm going to put it in the chat window for everybody. Okay. So David Wallace said by chat that he had a quick follow-up to one of the questions that was asked before. David?
Thanks. Yeah, it's a follow-up to Dave Baker's question to Eleanor. So I take the point completely that the relevant symmetry group is just the symmetry group of the entire theory. It's not the symmetry group of various component chunks of it. But of course, unless we want to apply this analysis to our sort of deepest theory of reality, which presumably we probably don't because it's not spatiotemporal at all, and in any case we don't have it, then the theory in question is going to depend on issues of energy scale and situations of interest and relative contingencies of emergence and so on. And that seems to give in your framework the conclusion that the structure of space-time is kind of quite theory relative, that relative to a certain approximation of energy scale, the structure of space-time is going to be one thing, and on different approximation of energy scale, or possibly in a different neck of the woods, the structure of space-time is going to be something different. I mean, that strikes me as an attractive rather than feature rather than otherwise of the account. But I just wanted to see if it was a feature you're happy with.
Yes, I mean, I don't think you know that, but yes, so I sort of didn't get fully in the emergent section to thinking about levels of space-time structure, and there's two senses in which we might have levels of space-time structure, and there's one that you gestured towards that I'm very comfortable with, which is sort of effective space-time structure at various levels that could be empirically relevant. And one of the things about obviously functional notion is that you can say, well, this is what fills the role of some approximation at this particular level. There's another question that I think is slightly thornier about what you do if you say, you know, you think general relativistic space-time structure is effectively valid at all phenomenological levels, and whether you then want to go and talk about space-time structure. There'll be a sense in which you might be able to talk about space-time structure at some other theory that has something akin to inertial structure in it, and then there's a question about the utility of that label. So there's different senses, and I'm very comfortable with the notion of levels of space-time structure that are relevant relative to levels of, say approximation or measurement. Slightly less comfortable and a bit more conflicted about the notion of levels of space-time structure that lose all empirical content or contact.
Great. So my clock says 4 o'clock, so we're just at the end of our time. So again, I want to thank our 3 speakers for their wonderful talks and for taking the time to answer everybody's questions. I want to thank everybody for joining us today. I'm glad we were able to get this going with a return for many of you of the academic terms. Please feel free to email me if you have any questions or suggestions about scheduling in particular. I know scheduling is particularly fraught for a lot of people right now for all kinds of reasons. And I guess that's it. Stay tuned. I'll be sending out invitations for the next mini workshop, which is the planning for which is already underway. And I just want to wish you all well and hope you're all doing safe and okay in the middle of everything. So thanks again to everybody.